So once we've learned information, once we've committed it to long-term storage, how is that information represented in the mind? What's the structure of knowledge in the mind? This lecture is based on chapter 8 in your textbook. So we think that knowledge in the mind is stored in the form of concepts. And concepts you can think of as mental representations of categories, events, and ideas. Storing knowledge as concepts allows us to recognize things and make inferences about their properties. Right? So looking at the different images on the screen of farm animals, which one is a cow and why? And when you recognize something as a cow, what else comes to mind? What does a cow make you think of? Right? So bringing a concept to mind leads to a whole bunch of additional information related to that mental representation. So concepts are organized in categories, and categories include all possible examples of a concept. Once we're able to categorize something, we know a lot about it. So categorization is arguably a good thing, right? Being able to look at things in our world and put them in categories is super helpful. So you see some sort of animal on the street, you look at it, you recognize it as a cat, and you put it into that cat category. And suddenly you have a whole bunch of additional information about it because you have categorized that concept, right? You know that cats have whiskers. They can be moody, they sleep a lot, they meow and purr. They like to be rubbed and they like affection. They catch mice, they like milk, and so on. So being able to categorize concepts, things that we see, things that we interact with in our world is super helpful because we get all of this additional information. So how do we do that? How do we put things that we recognize into categories? So one idea, one approach, is that when we see something in our world, we compare it to a stored representation known as a prototype. And you can think of a prototype as simply an average category member. So throughout your life, for instance, you've seen a bunch of things that are called birds. And in your brain, you've built up a prototype of what a bird is, what a bird should look like. And so when you see something that's similar to that prototype, you can quickly put that object, that animal, into that bird category, and suddenly, right, you have all this additional information about it. It may live in a tree, it flies, it eats worms, and so on. So categorization is super helpful, and the thinking is that we use this sort of prototype approach where throughout our lives we're sort of averaging across category members, and our representation for any category can be viewed as sort of an average, a prototypical representation of the category. Do we actually have evidence for this? So one thing we can do is simply ask people to rate different things within a category as to how well they actually represent that category, right? So if you take something like a sparrow, people will say that's a fairly good or very good representation of a bird. On the other hand, a bat is a fairly poor representation of a bird. And what we find is that objects, things, animals that we say are good representatives of their categories share a lot of features. Chairs and sofas are very good representatives for the furniture category, and they have a lot in common. Right? A telephone is a very poor representative for furniture, and so it has little in common with other members of the furniture category. So good category examples share many characteristics of other category members. What other evidence do we have that we use prototypes to categorize concepts? So we know from studies of reaction times that statements about objects that are close to prototypes are verified faster than statements about things that are pretty poor representatives of their category. So thinking about fruits, for instance, right? I think we would all agree that, an apple is a pretty good representation of a fruit. A pretty good prototypical category member. It's close to the prototype. And so when you're asked, is an apple fruit? You're very quick to say, yeah, yes it is. On the other hand, a pomegranate, much rarer. You rarely encounter pomegranates in your life. It takes you longer to say that a pomegranate is a fruit because it's further from the prototype. And then melon would fall somewhere in the middle. So objects, concepts that are closer to the prototype are easier to categorize, and we categorize them faster, and we can see this with reaction time studies. We also see that prototypical objects are affected more by priming. So if you recall, priming is a situation where the representation of one stimulus facilitates the response of another stimulus. So for instance, if you hear the word green, and you have to say whether these colors are the same or different, hearing the word green first will actually speed up your response here, because hearing that word has brought green to mind. Now, in the second case, these examples of green are further from a prototypical green. And so priming has less of an effect in this case. You hear that word green, the green that comes to mind is a prototypical green. And so we see greater priming for, prototypical greens, saying that these two greens are the same. We do that a little bit faster than this case because priming has less of an effect here. So we see that prototypical objects are affected more by priming, and that's, again, some evidence that we recognize concepts by comparing them to prototypes that we have stored in our minds. How is information organized in the mind? There are levels of categorization, right? We can talk about a global level, a basic level, and a specific level. So thinking about furniture, the category of furniture, that would be at the global level. And underneath furniture, we have examples of furniture. This is the basic level. So chairs, tables, beds. And then we can get even more specific. So we can talk about, dining room chairs versus kitchen chairs, kitchen tables versus dining room tables, single beds versus double beds, and so on. Typically speaking, we tend to operate at this basic level. So when you see something in your world, right, when you see a piece of furniture, you don't think, oh, that's a piece of furniture, or, oh, that's a lovely love seat. You think, that's a nice sofa, that's a nice couch. So we tend to operate at this basic level. Now, of course, if you have some expertise, let's say you're a car person, you see cars, you might, think more specifically, but generally speaking, we tend to categorize things at this basic level. And so I can just give you a quick example of that. So please name the following items. Right, so, this is clearly a bicycle, and that's probably what you would say if you saw this. But you could get more specific, right? You could say it's a single speed bike, but you probably wouldn't do that in this case. This is a house. You could get more general. You could say it's a structure, a dwelling, but again, we tend to not do that. We tend to operate at this middle level, the basic level. So again, in this case, you'd probably say that, this is a shirt versus a piece of clothing, which would be more general, versus a blouse, which would be more specific. And finally, here, you would probably say that this is a bird versus an animal or versus a sparrow. So, the take-home message is that when you see things in your world, unless you have some specific expertise, you tend to categorize objects at this basic level. How are concepts organized in the mind? So as we've seen, we can categorize things at different levels, right? The global level, the basic level, the specific level, we tend to operate on that basic level. The semantic network approach proposes that concepts are arranged in what we call hierarchical networks. And so the idea here is that more specific concepts are near the bottom of the network, and more general concepts are at the top of the network. So in this hierarchical network, we have living things at the very top, right? And as we move down through the network, we encounter more specific examples of living things, right? Animals, birds, fish, flowers, trees, and so on. And so we think that information is organized in the mind in semantic networks like this. Do we see any evidence for semantic networks in behavior? So one idea is that it should take longer to indicate yes to a canary is an animal than yes to a canary is a bird. And that's because there are more nodes. You have to move further to get from a canary is an animal to a canary is a bird. And so if we simply look at, reaction times to this question, is a canary an animal versus is a canary a bird, we do indeed see that it takes people a little bit longer to say that a canary is an animal versus a canary is a bird versus a canary is a canary, which we respond to very, very quickly. So greater distances between nodes are associated with longer reaction times. And so this is some evidence, right, that concepts are organized in semantic networks in the mind. If semantic networks explain how concepts are stored in the mind, then we should see that when one concept is activated, related concepts are easier to activate. So if I say the word robin or show you a picture of the bird robin, you should be able to respond faster to related concepts. So other birds, for instance, canary and ostriches, especially if those other birds look like robins, if they're closer to the prototype. And so this, to some extent, explains priming, right? We say that there's spreading activation. You've activated the concept of robin, and so that activation spreads to related concepts, and they become easier to identify. This idea has been investigated using word pair lexical decision tasks. And the idea here is that you see two words, and you simply have to indicate whether they are both real words. And what's quite clear when you do this task is that if the two words are related in some way, it's easier to identify them as real words. And this provides evidence for this notion that concepts are organized in semantic networks, and we see this spreading activation between related concepts. So when one concept is brought to mind, like a robin, related concepts are easier to identify. So here's an example using a word pair lexical decision task. So please read the following word pairs. If both words are real words, say yes, otherwise say no. Here we go. So hopefully everybody said no. Yes. No. Yes. Yes. No. Yes. And so hopefully you saw that, when the words were related like bread and butter, it was a bit easier to say that, yes, these are real words. And so we can test this in the lab. We can have subjects do this task over and over and over again. And we see that, yes, indeed, reaction times are faster when the words are associated in some way. And so that's what we see in this bar plot here. Associated words versus, so that would be like bread and butter, versus words that are not associated. So like phone and banana, for instance. Although maybe there's some association there. I don't know if you've ever held a banana up to your ear, jokingly, like a phone. Hopefully not. But the idea here is that retrieving one word from memory leads to activation spread that sort of pre-activates related words, and so they're a bit easier to access. They're a bit easier to pull out of your mental dictionary and identify. So one issue with semantic networks is that they do not explain why people are faster to say that a lion is a mammal than they are to say that a whale is a mammal. So to put that another way, semantic networks do not explain increases in reaction time for objects that are better representations of their category. Right? So under the semantic network approach, if two objects are the same distance away from a node, right? So lion and mammal are the same distance away from a node as whale and mammal, then we should respond to those two concepts equally quickly. So semantic networks as designed don't explain, the fact that it's a little bit easier to say that a lion is a mammal than it is to say that a whale is a mammal. It's a bit easier to put lion in that mammal category than it is to put whale in that mammal category. Now, if you can change the strength of connections between nodes, this problem is solved. And so this led to a new way to think about how information is organized in the mind, known as connectionism. And connectionism is an approach that's inspired by the makeup of the brain, right? So far in this lecture, right, we've been talking about the mind in a very abstract sense. We haven't really talked about neurons. Fundamentally, all of our cognition is grounded in neural firing. And so connection draws on the fact that neurons are connected and they have different connection strengths, right? As we learned in the lectures on memory, neural connections can be strengthened if we see repeated firing between groups of neurons. Their connections strengthen. So lots of interconnected neurons in the brain, and some of these connections are strong, some are weak. Connectionism draws on this to model how concepts are stored in the mind. And what's nice about connectionism is that it can explain how concepts are learned and how brain damage changes behavior. Connectionism was really pioneered by David Rumelhart and James McClelland. McClelland and Rumelhart worked at Stanford and Carnegie Mellon in the 1980s. So how do connectionist networks work? Connectionist networks are based on what's called parallel distributed processing. And generally speaking, this idea proposes that concepts are represented by activity patterns distributed across a network. And that network simply consists of very simple repeating units. And on their own, these units are almost meaningless. But together, specific patterns of firing represent specific concepts. And so we have one layer of our network that receives inputs, and one layer that gives us an output, right? So imagine that we want to categorize, animals. And so we have, robin, canary, beagle, and we want to put those animals into categories. So we input the animal, and we get some sort of output, right? Like dog, bird, for instance. So here's an example for the question, a canary is a, so we're inputting canary, and the information bounces around through the network, and this network has been trained in such a way that the connections between that particular input, canary, and this output, bird, are quite strong. And so we observe a pattern of firing that leads to the output that we want, in this case, bird. On the other hand, if we input beagle, the connections between that node, that beagle node, and this output dog are quite strong. And so that's the output we get in this case. Now, when we start with a network like this, all the connection weights are the exact same. So the first time we input canary, it might give us an output that's incorrect. It might tell us that a canary is a cat. And so we actually have to train the network. And so that's how you build these networks. You train them. You input canary. It tells you that a canary is a cat. You say, no, that's an error. And the connections between canary and cat are weakened. You input canary again. It says that's a horse. You say, no, that's an error. And the connections between canary and horse are weakened. You input canary again. It says canary is a bird. And you say, ding, 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 correct. And the connections between canary and bird are strengthened. And you repeat this thousands of times. And eventually, every time you input canary, you end up with the correct response. A canary is a bird. And so that concept in this case is represented by a specific pattern of firing that leads to a particular output. And again, you do the same thing for other concepts, such as beagle. You'd input beagle. It would tell you that a beagle is a horse. You'd say, no, that's incorrect. You'd do it again and again and again, and eventually the connections between beagle and dog would become very strong. And so every time you input beagle, you end up with the right response. And so by the end of training, each concept is represented by a unique pattern of activation. Right? So again, at first, you input a particular concept that you need to categorize, and this leads to output that's wrong. And with training, when you input that concept, you get the correct output. And that correct output, that pattern, is unique to that concept. And so by the end of training these networks, each concept is represented by a unique pattern of firing across the entire network. And this idea is to some extent at the heart of, machine learning. So if you use, for instance, a speech recognition system at home, like Amazon Alexa or Siri on your iPhone, it works in the exact same way, right? It has to recognize words, specific words. And when it starts out, it's very bad at that task, and they train it by inputting different speech patterns into the system and telling it that it's either, right or wrong in terms of how it categorizes the speech that it's hearing. And over many, many training trials, it'll give the right answer. You'll input a specific speech pattern, and it'll give you the correct response most of the time. So what are the benefits of the connectionist approach? Well, it's based on, the neurophysiology of how the brain works, right? So there's a plausible mechanism here. We know the brain is made up of neurons. Individually, these are very sort of dumb things, kind of like the nodes in these connectionist networks. We know the connection strength between neurons can change. So connectionist networks, although they're computer simulations, there's some basis for them in the brain. What else is nice is that damage to one part of the network doesn't stop the network from operating. So you don't lose the entire network by knocking out a few nodes, which is true of the brain, right? If you suffer a stroke, this might impact part of your behavior, but not all of your behavior. And these models are also very good at explaining generalization. So similar concepts like robin and sparrow, for instance, lead to similar patterns of activation. Now, the downside of this is that, some cognitive scientists view this approach as a reversion to behaviorism, right? You're inputting some sort of stimulus and you're getting a response. There's nothing sort of smart that's happening here. So connectionist models do not process information in the way that cognitive scientists envisioned, right? Via staged, rule-based operations. These models are arguably sort of anti to the whole sort of information processing approach. And so it's still debated, to what extent our behavior is the result of sort of the dumb interaction of neurons in the brain versus sort of higher level representations and rule application. Okay, so we've come to the lecture review. Question 1, what is a concept? What is a concept? Concepts are mental representations of categories and events. So for example, the concept of a cow. This brings to mind, everything that goes along with, being a cow, living on a farm, producing milk, and so on. How do we recognize concepts? That is, how do we put them into categories? Question 2, how do we recognize concepts? How do we categorize them? We likely compare concepts to prototypes. And as we saw, it's a bit easier to categorize concepts that are closer to prototypes in our mind, right? We're a bit faster to say that a sparrow is a bird versus a penguin is a bird. Question 3, what's a semantic network? Question 3, what's a semantic network? Semantic networks are hierarchical arrangements of concepts. So more general concepts are at the top, more specific concepts are at the bottom, and related concepts are connected in the mind. And semantic networks explain priming, right? If one concept is activated, we get spreading activation through the network to related concepts.